Hello everyone, I am Divya, working for the Department of Computer Science and Engineering, MIT, Mysore. In the previous class, we have discussed about basics of routing algorithms and along with that the classification of routing algorithms. Right? After that, we have studied about link state algorithm, which is used to calculate a least cost path from one source router to all other routers which are there in that particular network. Today, we move on to the next routing algorithm, that is distance vector routing algorithm. Okay. So, today's topic of discussion is distance vector routing algorithm. Okay. We have seen that there are several methodology or criteria which are used to classify our routing algorithm. In that, the very first criteria is what is the technique that is used in order to calculate the least cost path from one router to another router. Based on that, we had two classification. One is global, that is centralized, and another one is decentralized method of calculation. So, our distance vector algorithm falls under the second category, that is decentralized method of calculating the route least cost path from one router to another router. When I say distance vector routing algorithm, we have three things here. One is we say distance vector routing algorithm is distributive, iterative and asynchronous. So, what do we mean by this? What do we mean by distributive? Here in this algorithm, each router will have information about the least cost to the neighboring router. Okay, it maintains a table of distance from that particular router to the adjacent routers. So, at each iteration, what it does, it is going to exchange its information with the neighboring routers. With the exchanged information or with the information which the router gets from its neighbor, it is going to calculate the new values for its distance vector. So, here exchange of information is continuously happening between the routers. So, information is not global here, it is information is not centralized here, it is distributive. So, we call it as distributive. Then what do we mean by iterative? At each stage, whenever there is a change in distance vector that is stored for each router in the network, it is going to be calculated repeatedly. If there is any change, that is going to be intimated to the neighboring nodes and that is going to be recalculated using some equation, right, and again that is going to be updated, and updated information will be informed or propagated through message through to other routers here. So, it takes too many iterations to perform this. So, we call this as iterative. Okay. Then what do we mean by asynchronous? This algorithm, distance vector algorithm, never expects its routers to work in a locking system, means it never expects them to work in synchronous pattern. That is why it is asynchronous, right. One router calculates its information based on the information that it gets from the neighboring router, right. So, that is why we call distance vector routing algorithm as distributive, iterative and asynchronous. By observing these three things, we can say that distance vector routing algorithm is dynamic, isn't it? The values in the vector is going to be changed continuously, dynamically, depending on the values of the neighboring nodes or neighboring routers, right. So, that is why we can call distance vector algorithm as dynamic. Here in distance vector algorithm, every router will maintain a table of distance okay, table of distance which stores information about the distance or the cost that it takes for particular datagram to travel from that particular router to the adjacent routers. We call that table as distance vector. So, if we have nodes like x, y, z, then for each of these nodes we are going to have vector like this. From these nodes to these nodes, what are the route? X to x will always be 0, and what is the cost that it takes to travel from x to y, similarly from x to z, and similarly for other values. So, for each of these nodes which are there in the network, it maintains a distance vector. So, depending on the values that is calculated here, it is going to interact with other routers, and with the information that a router gets from its neighboring node, it updates its distance vector. That is how distance vector routing algorithm works. Considering that d of x y, let us consider d of x y represents the distance of least cost path, the distance in the least cost path from node x to node y. Okay. We make use of Bellman-Ford algorithm equation here. We make use of Bellman-Ford equation to calculate this distance, which is going to be stored in distance vector. So, d of x y, that is distance from node x to y, is calculated by looking at the minimum value which we get from this equation, where v is a vertex or v is any other node which comes between x and y. That is, if I have x, y like this, in between I might be having some t. Okay. In that case, distance from x to y is always the cost that it takes to travel from x to y, which is there, plus the distance that it takes from t to y. Okay. The minimum among them is considered as distance from x to y. Okay. Now, we will look into the algorithm in detail. Similar to our link state algorithm, here also in this algorithm also it has two steps or two phases. One is initialization and then looping. In the initialization phase, what it does? It checks for all destinations y in n, means for all the nodes or for all the routers that are there in the graph. N represents the set of nodes or routers in the graph. For all those nodes, assign a value of its edge. Okay. Distance from x to y is c of x y, cost that is associated for that particular edge, if they are directly attached neighbors. Okay. For each neighbor w, for each of the neighbors of x, okay, we are considering the node x here. For each of the neighbor of x, that is w, determine the value dw of y with the value that we have assigned here. Okay, and calculate that for all the destinations in n. Okay. After calculating the distance vector for all the neighbors of x, then for each neighbor w, send the distance vector. We have calculated the distance vector for all the neighbors, right? Now, send that particular distance vector to all the neighbors of x. So, this is the initialization phase. Then we will move on to the loop. Here it waits, it asks us to wait until I see the change, if there is any change in the link cost of the network, or if it receives any distance vector from its neighbors. Okay. Till that time there will be no least cost path calculation happening. Okay. Once it gets any updates in any two format which is specified here, either there should be a change in link cost or it should get some distance vector from its neighbor. In that case, what it does, for each y in n, means for each router that is present in the network, calculate the value for distance vector, okay, using the Bellman-Ford equation. This is the Bellman-Ford equation. Okay. Using this equation, calculate the distance vector. Once it is calculated, if there is any change in the value, we already had dx of y here, right. So, after getting new information from its neighbors, if there is any change happened after calculating the distance vector for that particular neighbors, if there is any change, then send the distance vector to all the neighbors. If there is no change, there is nothing to do with it. If there is any change, then send or inform the neighbors through sending a distance vector to all the neighbors, and keep on doing this forever. This converges at some point in time when there is no change happens at the network level. Okay. So, this is how the distance vector routing algorithm works. Now, we will understand how it exactly works with an example. Okay. We will look into an example now. So, to understand the working of distance vector routing algorithm, I am considering a simple graph or simple network with 3 routers, or graph with 3 nodes x, y, z, and cost of x to y is 2 and y to z is 1 and x to z is 7. Now, according to distance vector routing algorithm, we will start with initialization. So, at step 0, we will have distance vector for all these 3 nodes. So, 3 distance vector for 3 nodes. So, how it is for node x, similarly for node y, and for node z. So, how we are going to calculate the distance vector for these things. So, according to our initialization step, first we will look at its immediate neighbors. So, for x, from x to x there is no cost involved, so it is 0. From x to y it is 2, right. From x to z it is 7, right. So, first we are going to write the value or the weight of that particular edge for its immediate neighbors. Then, since we are considering it for node x, this distance vector for y and z will be infinity at present. Similarly, here y will not be knowing anything about x and z. We will calculate it for y. From y to x it is 2, from y to y it is 0, from y to z it is 1, right. And then here for x we will have infinity and for y we will have infinity at present, and for z, from z to x we have 7. from z to y it is 1, from z to z it is 0. So, this is the distance vector that we have at the initialization step. Now, what it does at step 1, this is for node x, and here we will have it for node y, and here we will have it for node z. Okay. What it does, after doing this, these 3 nodes, that is node x, node y and node z, they send their distance vector to all other vectors. Means node x sends its information to node y and node z. Here again we are going to have table like this. So, x sends its distance vector to y and z. So, we will copy this value here. For x we have 0, 2, 7, and here it is 0, 2, 7. Similarly, y will send its distance vector to x and z. So, we will copy this value. Here value of y is 2, 0, 1. Here it is 2, 0, 1, right. Similarly, z sends its distance vector to node x and node y, right. So, we will copy this value 7, 1, 0, 7, 1, 0. Now, if we consider node x, we have value of distance vector from node y and node z. Making use of this value, we are going to check whether the distance vector that we have for x at step 0 remains same, or if we are going to get the new value. From x to x it is 0, from x to y what are the paths? Initially we had x to y as 2, right, x to y is 2. There is one more path to reach y from x, that is x to z and z to y, right, x to z and z to y. If we consider this as v, so d x of y is equal to c of x v plus d v of y. That is the case c of x z. What is the c of x z is 7 plus d v of y means d z to y. So, what is that? D z to y is 1. So, that becomes 8. We already had 2 and new calculated value is 8. So, which is the minimum among these two? It is 2. So, what we will write? We will write from x to y as 2. We will retain the value as it is. Similarly, we will look out for the paths for z, x to z. We already had a value x to z as 7. Is there any other path to reach z from x to y and y to z, right? We can travel from x to y and y to z. From x to y it is 2. From x to y we just calculated it is 2 plus from y to z means from y to z we have 1. So, it is 3. We had 7 and newly calculated value is 3. Which is the minimum among them? Minimum is 3. So, what we will do? We are going to change the value of x to z from 7 to 3 here. So, now our distance vector is changed for x. Similarly, we will calculate the value for distance vector for y and z. Okay. How? from y to x, again we had y to x we had 2, right, in our initialization state. From y to x we have 2. Is there any other path? From y to z and z to x we can travel, which will cost y to z is 1 plus z to x is 7, which is 8. So, minimum among them is 2 and we already had 2 here. So, we are going to retain the same value. From y to y it is 0. From y to z we have 1 here, right. Is there any other path to travel? From y to x and x to z we can travel. So, that costs from y to x. From y to x it is 2. From x to z, from x to z it is 7, that will cost 9, but minimum among these two is 1. So, we will write 1 here. From y to z is 1. So, our vector for y is not changed. Here also it is 2 0 1, here also it is 2 0 1. Similarly, we will calculate distance vector for z depending upon the distance vectors that we have here. Okay. So, from z to x we had 7. Is there any other path through which we can go? From z to x we have 7. We can go to y and then from y to x. So, from z to y, what is the value that it takes? From z to y it is 1. From y to x it is 2. So, that becomes 3. Among 7 and 3, 3 is minimum. So, we will take 3 as the value. Similarly, we will calculate value for z to y. Okay. Z to y we have already 1. Is there any other path from z to x to y? We can travel from z to x and then to y. Z to x we have 3, sorry, z to x we have 7. We need to consider these values, right. From z to x we have 7. From x to y we have 2. So, that is 9. So, minimum among these two is 1. So, we are going to write 1 here. From z to z it is 0. So, now looking at the distance vector at step 0 and step 1 for z, here it was 7 1 0. Now, it has been updated to 3 1 0. So, this is also changed. So, what should we do in the next step? In the next step, whatever changes that happened, that is going to be propagated to the next step. Here again we have distance vector for x, y and z. So, this is for x, this is for y and this is for z. Okay. So, now our distance vector for x is changed. So, distance vector of x is propagated to y and z. So, we will write distance vector here 0 2 3 0 2 3, okay, and our y haven't changed anything. So, it is not going to propagate any message to its neighbors. Distance vector of z is changed. So, we will intimate these two x and y. So, z 3 1 0 3 1 0, y is not changed. So, new information will not be updated. Whatever value we had initially will be retained as it is. Right. So, now based on the value that it gets from these two distance vectors, it is going to calculate value, new value for itself. So, for y we have 2 0 1 here. Based on these two values, we are going to calculate the distance vector for x. From x to x it will be 0. From x to y we had 2 here and we have 2 here, and new path will be x to z to y. So, what is the value from x to z? It is 3, plus from z to y it is 1, which is 4, but 2 is the minimum which we already have. So, we will retain that value. Now, we will calculate the value from x to z. From x to z we have 3, already we have 3. Now, we will calculate, is there any other path through which we can travel. From x to z we have 3, x to y and y to z. So, x to y and y to z. So, what is the value from x to y? X to y it is 2. From y to z, it is 1, which is 3. So, there is no change in the value. So, we will retain it as it is. Again, we are going to calculate the value for y here. Since the value of x and z is changed, okay, we are going to calculate distance vector for y here. So, how to calculate it? Same procedure, okay. From y to y it will be 0. From y to x we had 2 in our previous step. Is there any other path through which we can travel to x from y? From y to z and z to x, right? Y to z and z to x. So, what is the value from y to z? It is z to y to z is 1. From z to x, from z to x it is 3, value is 4, which is minimum, it is 2. So, y to x is 2, right. From y to z we have 1. Is there any other path? Y to x and x to z is the other path which we can have. So, what is the value of y to x? From y to x we have 2. From x to z, from x to z is 3. Hೀಗಾದರೂ ತಗೊಳ್ಳಿ, ಹೀಗಾದರೂ ತಗೊಳ್ಳಿ. From x to z it is 3. So, it is 5. So, which is the minimum? This is the minimum among them. So, this remains same. The distance vector for y also remains same. Distance vector for x also remains same. Now, we will calculate the distance vector for z. For y we have 2, 0, 1. So, how to calculate it? From z to x we have 3 in the previous step. Now, is there any other path from z to x, z to y and y to x, right? Z to y and y to x. So, what is the value from z to y? From z to y, that is 1. From y to x, it is 2, that is 3. So, the value of z to x never changed. So, it is 3. From z to y we had 1. Is there any other path? We have z to x and x to y. So, z to x it is 3. Z to x it is 3. From x to y it is 2. ಹೀಗಾರು ನೋಡಬಹುದು. From x to y it is 2. So, it is 5. Okay. So, right. So, minimum is 1. So, we have 1 here. From z to z it will be 0, right. Now, if you look at the distance vectors here in this step and the previous step, distance vector for x is same, distance vector for y remains same, distance vector for z remains same. So, there is no updations in the distance vectors of x, y and z. So, the algorithm converges here. So, until there is any change in the cast of the link, in the least cost path from x to any other vertex, the value remains same. So, until there is no change in the value of distance vector, there will be no message propagation happening. So, the algorithm continues until there is no further changes happening in the distance vector of that particular node. So, this is how we are going to calculate the routing table for node x, y and z with different iterations, right. This is how our distance vector routing algorithm looks. Now, having a knowledge of how distance vector routing algorithm works, we will see what are the consequences or what are the effects or what are the fallbacks that we can have in case of distance vector routing algorithm. So, in distance vector routing algorithm, we said if there is any link cost change happens, then it is going to recalculate the value for its distance vector and the newly calculated distance vector will be informed to its immediate neighbors, right. So, what happens here, we come across two scenarios. The very first scenario is if link cost goes down. The second scenario is if the link cost goes up. Taking the same example of 3 nodes, here we have 3 nodes x, y and z with the value 4, 1, 5. Here if the value of 4 goes down to 1, what will happen? Here if the value of this link x, y was initially 4 and distance vector was calculated for that particular node at that particular point in time. At some instance the link cost, the link x, y cost for this link goes down from 4 to 1. So, the newly arrived link cost will initiate the process of calculation of new distance vector for x, right. So, when y comes to know at time t0, y will come to know that there is a drop in the link cost of y to x, right. So, it calculates its new value dx of y using the same Bellman-Ford algorithm, Bellman-Ford equation. Once it is calculated, it changes its value from 4 to 1. Initially we had dx of y as 4, now it has come down to 1. So, which is the new value that we are going to have? In order to reach x, we have y to z and z to x path. So, y to z we have 1, from z to x we have 5 here. So, it is 6, right. So, in order to reach x, we had 4 and the new link cost is y, it is not going to affect this particular route. So, it is directly changed to 1, right. So, there is no problem happening here, and once the distance vector is calculated, it is going to inform its neighbors about the change in the link cost and change in the distance vector. So, it informs z as well as x. So, at time t1, what will z and x do? They will receive the information from node y's distance vector and they updates their respective distance vectors. So, that is not going to do any much change here, okay. It is just going to update the value and no problem will persist here in this case. But in the second scenario, if the value goes up from 4 to say 60, from 4 to 60, what will happen? Initially we had some value as 4, now for some reason, might be due to congestion or something, it has raised up to 60. So, dyx is directly raised up to 60. the same information is propagated to its neighbors, that is x and z. So, new distance vector will be calculated for z as well as x depending on the value of distance vector of y. So, while calculating this, at every iterations the distance vector keeps on changing, okay, it keeps on changing. So, that leads to count to infinity problem. Okay, that lead to count to infinity problem. Okay. So, in order to avoid this problem or in order to address this problem, we have Poisson reverse method. So, what is this Poisson reverse method? In case of Poisson reverse method, what it does, when the value goes up from 4 to 60, we have x to z as 5. For some reason this might become 50, okay, this might become 50, but so the link cost that it takes to reach from x to z is 50, and if it comes through y, it will become 1 plus 60, that is 61, right. So, to avoid confusion or to avoid count to infinity problem, this d of x to z is considered as infinity here. So, even though there is a path, through which y can reach x, that is 1 plus 50, instead of 60, y can take this route 1 plus 50 which costs 51, but that might lead to count to infinity problem. So, in order to avoid that, d is x of z, this is kept as infinity, this is made as infinity in the distance vector. So, by looking at it, it will compare the value. So, in y, in order to reach x, it is having 60 as its link cost, and if it pass through y, sorry, if y passes through z to reach x, it will cost 1 plus infinity, which is again infinity. Comparing 60 with infinity, 60 is the lesser cost. So, it will take the same path even though it is of higher link cost at this scenario, but this avoids count to infinity problem in this particular network. But let us think, is this is a permanent solution for count to infinity problem? No, certainly not. For few instances, for few scenarios, this Poisson reverse method helps us to avoid or encounter count to infinity problem in case of distance vector routing algorithm. So, these are the concepts or information that we have to understand about distance vector routing algorithm. Now, having studied about link state algorithm and distance vector algorithm, let us try to understand the difference between them. Okay? That is your next topic. So, our next topic of discussion is the difference between link state routing algorithm and distance vector routing algorithm. Considering n as number of nodes in the network and E as number of edges or links in the network. Okay, we will try to understand the difference between link state and distance vector algorithm. The major difference is the methodology, right. The link state vector machine forces us to know all the entire information about the network and the linkers between each of the edge from one source to all other routers in the network, right. That is the prerequisite in order to execute our link state routing algorithm. In case of distance vector algorithm, it is not like that. It starts from one point, it keeps on upgrading the routing table as and when it gets the information. So, link state is centralized whereas distance vector is decentralized algorithm. This is the basic difference that we have between these two. Apart from that, we will discuss the difference in 3 criteria, with respect to 3 criteria. The first one is message complexity. The second one is the speed with which the algorithm converging. Third one is robustness, which is more robust. Okay. So, considering these 3 criteria, we are going to discuss the difference. Let us consider the first one, the message complexity. As we all know, in case of linked state routing algorithm, if we start from one source, say X, and we will be having Y, Z, T, U. So, we will be having several other routers in the network. At each point, at each iteration or at each step, this particular node X need to send information to all the routers that are there in the network. Either it can be a directly connected router to this source, or it can be connected through some other routers, right. From Y we might get connected to S, from Z we might be having some other routers like this. So, message broadcasting need to be done from a source vertex to all other vertex at each step. So, message broadcasting, the complexity of message is high, and as I already told you, this source vertex X need to have a complete information about the link cost, that is the cost that it takes in order to travel from X to all other vertex or all other routers that are present in that particular network. So, the complexity of messaging is more in case of linked state, whereas in case of distance vector methodology, what we do, the router is going to send its distance vector to its immediate neighbors, directly attached neighboring routers, and it takes information from the immediately available, that is directly attached neighbors, and based on that information it is going to calculate a new distance vector, which is again means broadcasted back to other directly attached routers. So, here communication takes place only between directly linked routers in case of distance vector, whereas in case of linked state it is with all the routers which are there present in the network. So, the message complexity is more in case of linked state. Okay. Coming on to the second criteria, that is speed of converging. In linked state algorithm, once we start finding the least cost path from one source to all other vertex, once we find the least cost, it remains unchanged until there is any change in the link cost happens in between. Okay. Due to some network issues or due to some other criteria, if there is any change in the cost between any two routers, then it is going to be recalculated, otherwise it is going to converge, or it is algorithm is going to end up easily. Whereas in case of distance vector, it is not like that. The distance vector value keeps on changing for each router dynamically, right, as we have already seen, right, and sometimes it might also leads to the problem of count to infinity, right. So, in that aspect, the speed of converging is better in case of linked state, whereas it is not in case of distance vector. Okay. The third criteria is robustness, which is more robust. Suppose in our network, if there is any mishappenings happens and if any router get corrupted, in that case what happens, that router might send wrong information to all its neighboring routers about its link cost, right. In that case, linked state algorithm does not get affected easily, because it can follow other routes to reach the destination, but it is not in case of distance vector, because as we know, at every iteration in distance vector a new value will be calculated only depending on the information that it receives from the neighboring router. So, if corrupted router sends some wrong information to its adjacent routers, then the new value that is calculated in order to find the least cost path will be wrong. So, the robustness is also more with respect to linked state compared to distance vector. So, these are the three difference between linked state routing algorithm and distance vector routing algorithm. So, to conclude, we have studied two algorithms so far, that is linked state and distance vector algorithm. In the next class, we are going to discuss about hierarchical routing algorithm, and we study more about routing with routing in the network with a broader perspective. So far we have discussed routers within a small network. In the next class, we are going to discuss it with a huge network which contains so many small networks within it. Okay? So, we will study that in hierarchical routing algorithm. Okay? So, this is the conclusion of today's class. Thank you.